Ladies and gentlemen, welcome to the Shaw Prize Lecture in Astronomy 2024 hosted by the Shaw College of the Chinese University of Hong Kong. May I first invite Professor Leung, Head of Shaw College, to deliver his welcoming address. Professor Leung, please.
Professor Kulkarni, Professor Genso, distinguished guests, colleagues, students, ladies and gentlemen, good evening. Welcome to the Shaw Prize Lecture in Astronomy 2024. I am delighted to see many enthusiasts in astronomy here today. The Shaw Prize was established in 2002 under the auspice of Sir Run Shaw to honor individuals who have made outstanding contribution in academic and scientific research or application. Since the first Shaw Prize presented in 2004, Shaw College has been selected to host the Shaw Prize Lecture every year on one of the three prizes, astronomy, life science and medicine, or mathematical sciences, through presenting lecture of the Shaw Laureates for professional, students, and the general public. We strive to uphold Sir Run Shaw's vision on the pursuit of knowledge, as spelled out in the founding aspiration of Shaw College: learning, innovation, and benefiting humankind. I would like to congratulate Professor Kulkarni for his achievement in astronomical discoveries. We are very honored to have Professor Kulkarni here today to share his groundbreaking findings of the universe and its wonders. I have to be honest, I am a psychologist by training, so I know nothing about astronomy, and I should not pretend to know anything about astrophysics. And we are very happy this evening and grateful to have Professor Chung from the Department of Physics to introduce our Shaw Laureate in astronomy and moderate a Q&A session later on. May I now pass the time back to our MC.
Thank you, Professor Leung. May I now invite Professor Chung from the Department of Physics of CUHK to introduce the Shaw Laureate in Astronomy 2024. Professor Chu, please.
Professor Leung, Professor Genso, Professor Kulkarni, distinguished guests, colleagues and students, it's my great honor to introduce our speakers today. Recipients of the Shaw Prize in Astronomy 2024, Professor Shrinivas Kulkarni, for his groundbreaking discoveries in many things. Millisecond pulsar, gamma ray bursts, supernovae, variable and transient astronomical objects, and many other things. The Shaw Prize Foundation recognized his contributions in time domain astronomy, particularly in the conception, construction, and leadership in the building of the Palomar Transient Factory, as well as its successor, the Zwicky Transient Factory. Professor Kulkarni is currently the George Ellery Hale Professor of Astronomy and Planetary Science at Caltech. He received his bachelor and master degree from Indian Institute of Technology, Delhi, 1978, and then his PhD degree in 1983 from UC Berkeley. He joined Caltech as a faculty member in 1987, and he served as the chair of the Caltech Optical Observatories from 2006 to 2018. As a member of the Royal Society of London, Indian Academy of Sciences, the Royal Netherlands Academy of Arts and Sciences, as well as the US National Academy of Science. Professor Kulkarni has received many awards. It's a long list of them, which I won't read out all of them. But rather, I'd like to add a personal note. Palomar Transients Factory, Palomar. When I was a high school student like you in Hong Kong, I organized the astronomy club, and we would do stargazing every week. And I heard of the name Mount Palomar, Palomar Observatory, every week. It was like the center of the universe for me for astronomical research. So it was really my dream when I was like your age, that one day maybe I could go to Palomar and do some observations there. I actually realized that dream when I was a graduate student. But that was the reason why I went to Caltech for my undergraduate study. So Professor Kulkarni is like a hero to me for reviving Palomar. It is also at the forefront of astronomical research today because of his work transforming some old telescopes and old observatory into a powerhouse, making discoveries after discoveries after discoveries of many exotic objects. So it's with great honor that I will invite Professor Kulkarni to deliver his talk tonight. Thank you.
Okay, so the talk today is on the dynamic night sky. And many of you sort of may have this idea that you go some mountaintop, it's a clear night, and the stars are twinkling, life is very peaceful, and nothing changes. It seems forever. Unfortunately, if that was really happening, you and I won't be here, and that is a start of our story. That it is the changes in the universe that, in fact, bring elements which make the periodic table. And once you get those elements, then chemistry starts, and then once the temperature is reasonable, biochemistry starts, and then sometimes biochemistry leads to life, and then sometimes it leads to intelligent thinking and the ability to actually see the whole thing, okay, which is, to me, very astonishing. So I've divided this talk into a smaller part first, which is I'll give you my view of what is science, and then it's followed by sort of the main project itself, okay. And I've been, I think, allocated 70 minutes, but I really hope I can finish it in 55 minutes so that there'll be more time for discussion, because in my mind, if you want to do science, you must be able to discuss and debate very courageously and freely. The way not to do science is to actually involve your ego into it. And in fact, I can tell you, having been in the science world for a long time, more than 4 decades, this is something that many people who are older still have it, okay? So you want to be a good scientist, you have to be able to think very clearly and fearlessly, okay? So I'm expecting, and I'm looking around at all the young people, that you will stand up and ask some question, even if you think it is not so great or stupid or something. It's a question you ask because you haven't understood something, or you're very curious to know something, okay? Okay, good. And if you don't do that, I'll simply point at one of you and then say, okay, you stand up and ask questions, okay? And so either be prepared for one or the other outcomes now. Okay, so what is science? So first, I'll give you my view of what is science, and it's somewhat different, I would say, than what popularly read. And this could be a part of the discussion, because I'm going to challenge you. I'm giving you my view, and it'll be hopefully so different from what you've been thinking, you'd be really offended, then you'd want to discuss with me, okay? So in my mind, science has 2 main branches. One is phenomenology, Other is physics. Not physics as a subject, not physics as a department, like the way you think. I'm talking of very two different ideas of what is physics and what is phenomenology. So let me explain that. Okay, so for this slide, at least pretend physics is not a subject. It's some sort of a concept, which I'll explain. What is phenomenology? It is very expansive. It has three distinct steps. So the first step is exploration. Phenomenology is trying to look at the world as it is. When I say the world or universe, it's different for different people. If I say, let's look at the world as it is, it may be the continents, or it could be you go into a jungle and you're interested in insects. That's the world of insects. Or it could be the universe, which is the world of astronomers. Okay, so the first one is collecting data. It's just to know what is out there. Okay, it's a very important part of phenomenology, which is you're not coming up with some preconceived ideas of what the world should be. You are being informed by data. So sometimes it's now called as data-driven science. Well, this is to do the science, you've got to get data. So step one, collect data. And sometimes people make fun. He'll say, oh, this is called butterfly collecting. Well, that's true. I would love to collect butterflies. There's so much amazing to understand the diversity in these butterflies and what causes it, okay? The next one is you get all this data, but you need to put this into some organization, okay? And that is sorting into families. So let me give an example. You go to Costa Rica. Apparently it has very nice, rich jungles. So you get a camera and you start taking pictures of various insects, birds, what have you. And then let's stick with insects. You find there's some insects which fly, there's some insects which actually just live on the surface. Now you're making them into families. And the last one is to actually start seeing patterns, okay? This is a bit harder in biology. It's finally we are getting to the point of what I'd say there is a subject called maybe theoretical biology coming, but physics was much easier, followed by chemistry. So usually it's much easier to discuss this sequence in physics. Because higher the energy of the phenomena, the simpler are all these things actually. And lower the energy there's more complexity. Okay, so what are examples of phenomenological subjects where this three-step process happens? Astronomy is perhaps the oldest, then botany, biology, geology, all these subjects which are essentially informed by data. Physics is a very interesting idea, actually. It's completely the opposite. One expands the data, classifies, and then reduces it a little bit. But physics is to reduce everything to its absolute distillation, its minimum value. Okay, so for example, the grandest one is the universe. Okay, can I say the most basic things of the universe in the fewest numbers? And the answer is 7. Okay, it turns out the geometry of the universe we can now summarize in 7. Okay, and it has some underlying internal relations, but the 7 numbers are distinct. And after that, you can basically say this is how the universe will evolve. It's geometry, it's change in energy to matter mix, and so on. Okay, that's the power of physics, complexity into a distillation. Okay, but inherent to all of sciences is physical models. When I use the word physical model, I mean in the sense of spirit as a reductionist approach. So there is no science, if you don't have a mathematical statement of what your model is, you don't understand it, okay? That is the most basic statement you can make. The step before that is if you can't measure it precisely, you don't understand it also. Okay, so all physical models are basically mathematical statements with some free parameters, which you don't know why they are, and eventually you want to understand that too. So I told you the universe is 7 free parameters. We don't know why the Hubble constant is this, why the universe is 13.4 billion years, but given those 7 parameters, I can tell you many, many things. Okay, the fewer the number of equations, mathematical statements you make, and the fewer the number of free parameters, then the more complete and more powerful is your understanding. Okay, so you should be amazed that astronomers have come to the point of describing the large properties of the universe with only 7 numbers. Okay, but this is all sounds very general. Now I'm going to make it rather specific, okay? And the specific, to give an example of how we went from phenomenology to physics, and astronomy here plays a very big role. Okay, so let's say we go back 10,000 years, maybe. Humanity everywhere in many continents noticed that sky, which is inevitable when you go to sleep in the open, that there are things in the sky, and very quickly they found a pattern. And the pattern is the bright objects which are fixed with each other, and the other fewer bright objects which move with relate to the fixed objects. The fixed objects, which means they have the same pattern, like the Orion big rectangle. It's a rectangle this year, next year, and the year after that. It moves on the sky. But the other less than a dozen objects were bright, and they moved with respect to this, and those are the planets. Okay, then after a while it was noticed planets show periodicities. Okay, you look at Venus, it seems to come, go to east and west and comes back. And okay, so this had been there for a long time. Then in the midst of the, Brahe undertook a lifelong study of positions of planets with respect to stars. Now, Brahe had an observatory. It was off the coast of Denmark, and he somehow managed to convince the king of Denmark to invest very big amount, which if you compute in modern terms, about 1.7% of the annual GDP for 1 year of Denmark into his observatory, okay, at Uraniborg. And obviously the operating funds for the rest of his life. They were done very meticulously, okay? And, he realized that that was all he could do. But he handed off the data to Kepler, and Kepler looked at this massive data. Okay, so we already have done the butterfly collecting. We know they're planets as opposed to stars. And he looked at these planets, and he reduced all that data into 3 laws. The law of ellipsis, that these planets move in elliptical orbits with the sun at one focus. Okay, it's a precise mathematical statement. Law of equal areas. Each planet, if I think of a planet moving like this, it's covering a certain amount of area per unit time. Each planet sweeps an area that is the same throughout the orbit, so the areal coverage is constant. And the law of harmonies is the square of the orbital period of the planet is proportional to the cube of the orbital radius. Okay, this is physics at its best, and this is a real physical model because these are all mathematical statements. Okay. But to actually get to the next level took a few hundred years. It required the development of Newton's theory of mechanics. Okay, Newton's theory of mechanics. We have velocity, we all understand that. We get in a car, you can see a little speedometer, and we also know what is acceleration. If you press the accelerator, you go a little faster. Okay, so now you have to look, these are mathematical statements, which is velocity is simply the change of position with time, dx by dt. dx is change in force over time dt, okay? Acceleration is a change of velocity with time, so dv by dt. But velocity itself is the change of position, therefore acceleration is the second change of position with time, okay? And it's written in this very beautiful equations here. And then Newton's great understanding was that the force is equal to mass times the acceleration. And then during a COVID-like situation, he went back to Cambridge. So from Cambridge to his home, and the apple fell on his head. Most of us would have just eaten the apple, but he said, why did the apple fall? And then he figured out that the moon is attracted by the earth, and yet it doesn't crash into that, and that's where he realized there's a force of gravity, and then there's a centrifugal force, and so on and so forth. So he came up with this Newton's law of gravity, which is the force between two bodies is proportional to the product of their masses divided by the distance square, and it's radial. Well, I would say, to me, this equation is like really amazing. I know that Many of you may think, Shakespeare something or some other classical music something is very deep and moving. Yeah, fine, it's okay. If you know English, maybe Shakespeare something is fine. But if you like rock music, why would you think any classical stuff is going to be moving? This, on the other hand, is universal. It's not universal to all civilization on Earth. It's the same on any other extrasolar planet civilization. Okay, this is really deep and moving. This is the truth. Okay, the rest is just your amusement. Anyway, so the solution to this equation now required the development of invention of calculus. Okay, this is Newton, Leibniz, also the Kerala School of Mathematics and Astronomy. Only when this was done, you could solve this and derive and explain the three laws of Kepler. And they go back to understanding very clearly why it's an ellipse, why the rate is that relates to the conservation of angular momentum, and why in this particular equation you get the p squared and a cubed relation. Okay, so I've given you a very clear and definite view of how I'm looking at it, mainly to challenge some of you who love classical Western music to get so mad that you'll ask me a question and try to say, no, that's better. In which case, I'll allow nothing more than a discussion with you. Okay, so let's now try to wrap up this part. In my view, for phenomenological sciences, the discoveries constitute the blood of science. Okay, you have to go and discover things. And in order to do this discovery, it's not something you can sit around and think. Okay, and I'll come back to why I'm saying such strong words. You have to go build gizmos, you have to build telescopes, microscopes, spacecraft, whatever it is, to go and discover the universe as it is, which means it's technology. So my view is very simple. It's not so much that, we had this wiki transient facility and there's some genius thing we did. No, it's building the gizmo. And then inevitably, unless you're not all that bright, that machine will start finding things and you just have to pay attention and you'll make the discoveries. The hard part is step one, okay? So I'm not a big fan of, I had this idea. Ideas are cheap, actually. Taking an idea through execution is not at all cheap. In fact, that is what differentiates a successful scientist from most scientists who take an idea, think it's interesting, write a little paper, and then when someone like me is giving a colloquium like this, will say, back in 1952, I had this idea. Okay, it doesn't mean a thing, okay? Because if you had this idea in 1952, you should have made the discovery in 1953, or keep quiet about it. Okay, so the second thing is mathematics is the language not only of physics, which physics is really the fundamental science. So it's the language of science. It's a very simple statement. So in fact, I would go and claim maybe the one true universal language, is actually mathematics. That is, let's say there's another civilization on another planet. How would they be developing physics? I don't know. Maybe they won't use differential equations. They'll have a more geometric approach. I have no idea. If I knew that, I'd be a brilliant mathematician, okay? But the number theory will be the same, and so I'm quite confident mathematics is the language of the universe. Finally, computational methods are really required to solve, okay, these problems, because not all of them will be analytical. Okay, why am I saying all this on a talk on the exploration of the universe? The reason is, I have been very strongly driven by the idea that we should go and discover the universe as it is. And I really absolutely am against the idea that you can sit around and contemplate and things will happen. Unfortunately, in the last 30, 40 years, there's a whole development in, unfortunately, physics. And this has gone to do with things which is essentially what you wanted to say, where you don't understand. Astronomers have told physicists, okay, there's something called dark matter, yeah, and something called dark energy, yes, and we don't know how, why, and all that. So that has given free rein to the ideas that you can discover these things by purely mathematical methods, okay. And my view is, not only just my view, the record is clear. There's been zero progress in this field for the last 40 years. These people write papers endlessly, one after another. And I hope, and if there are any students working on astroparticle physics, particle astrophysics, please be careful. You may not be using your life very well. Okay? Okay, so you do not discover the universe by sheer contemplation. I can assure you of that. If the universe was born with perfect symmetry, if there are no fluctuations in the matter-energy field, there would be no structure later on. So amazingly enough, it's the imperfections that matter, and this you can't figure out from first principles. Okay, enough of the sermon. Now let me go on to the main topic. And that's the story of the periodic table. That's the colloquium today, okay? Time domain astronomy touches on many, many aspects of the universe, so I can't focus on many other things like gravitational wave sources, for example, which is a very big part of, exciting part of time domain astronomy. Stellar evolution, that's another exciting part. So let's focus on the periodic table. Let's look at the story of the periodic table. Now we have it on very good data and model that when the universe began, it was very hot. The quarks all condensed. They made protons, neutrons, electrons. And then as the temperature cooled down, nucleosynthesis ceased. So we had basically at this point, the end point was mostly hydrogen, about 10% helium, very small amount of lithium, and that's it. Okay? So the universe begins with 90% by number hydrogen, 10% of helium, and then as it cools down, hydrogen becomes, the proton gets electron, becomes hydrogen, helium gets 2 electrons, becomes a helium atom. Okay, there we are. That's how the universe began. So I ask you a very simple question. Let's look at your own body or the crust of Earth, and you see there's a huge difference. How did you go from this to this? Okay? How did this happen? And this happened because stars lived and died. It is stellar death which starts building up the periodic table. It's stellar life that starts building up the light elements. There's a sequence here, and the stellar death builds up the heavy elements. Stellar death happening twice builds up even the heaviest elements. And that's one of perhaps the main driver to do time domain surveys of exploding stars. Okay, so this is an example where, there's no pure thought here. This really requires you to actually understand the details. You really have to actually understand nuclear physics very well. You have to understand gas dynamics very well. You have to understand how stars are formed and how gas mixes up. So this is something where the problem is very well laid out, and we don't have the imagination and detailed understanding, and therefore we have to get data. And that we do through observations. Okay, so what the Zwicky Transient Facility and other such surveys do is actually very simple. I can tell you the methodology. It's not difficult at all. So we take a picture, let's say last year I've been taking pictures of the sky. I'll call it as the old picture, okay? Let's use the old picture. I take a picture tonight, and then that's a new picture, okay? And then I find once in a while there's a new star. Okay, you can see there's a new star. That wasn't there before. And that's it. That's all we do. It's nothing more than that. I mean, how simple can this be, right? Now, there's a lot of details here because these are not perfect pictures. The weather conditions may not be the same. And here it's easy because the field is not very crowded. This is a resolved galaxy. So there's a lot of real details which requires algorithms, instruments to actually reach a very high level of performance. But this is what a supernovae looks like. It's a new star that comes up, and sometimes it shines as much as the rest of the galaxy, even though it may not be apparent here. You can take it from me. For a few weeks, it may be as bright as the rest of the galaxy. Okay, so the Okay, so the idea of looking for variable stars has been around a long time. Maybe it goes back to about 150, 180 years. Okay, but the idea of studying the sky systematically goes to Zwicky, who was the first physics professor appointed at Caltech about 1926-27, when George Ellery Hale, who founded Caltech, who was a mastermind for the 60-inch telescope at Mount Wilson, the 100-inch telescope at Mount Wilson, which is where the expansion of the universe was discovered, the size of the galaxy was measured or inferred. He decided to work on the 200-inch program, which became the Palomar telescope. And Caltech decided they really needed a sort of an astrophysicist, and they got a Zwicky. And in my mind is I have a few heroes of the last century. And I would say, first of all, he is like the most amazing astronomer from Pasadena area. There are other few lesser known people. But he was really amazing. He was a theoretician, he was an observer, he was an experimentalist. He held fundamental patents on jet engines. When World War II came about, he started working on fluid mechanics. Okay, so working with another astronomer, very famous, called Bardet, they discovered by the mid-30s, they discovered that that these new stars that come along can be classified into two. So now again we see we are into the empirical phase of this analysis. So you can put them in a diagram, which is called a phase space. I simply will sometimes call it as a Zwicky diagram, which is how long does that transient live, okay? And how bright is it? Now, I won't try to explain the negative numbers and so on. It's basically minus, if for students, I'm sure all of you are, okay, it's very important you have to know mathematics, so I'll assume you know this. It's minus 2.5 log of something, okay? That's why it's a negative number. They found that there are two kinds. The novae are frequent explosions, are what are called nova, simply meant nova stella, shortened to nova for new star, and supernovae, which is supernova, except when it was first used, it was super dash nova. It's a new word at that point, but now it is in the English language at this point. So it is about 10,000 times brighter. So there's this sequence here where there are these other things, supernovae, and these things. So Zwicky had many interesting ideas quite ahead of his time. So let me first tell you the answer already of how the periodic table got built up, and here it is. So you can see this periodic table. Okay, hydrogen and helium, they're basically made when the universe begins, and the rest were all made for different processes. So for example, let's look at this. Exploding massive stars, okay, they make much of the light elements and some of these things that come a little later. Exploding white dwarf, well, that's a very big contribution for making iron, okay, this up to the iron, that's a major source, okay. And then finally you have to go to things like merging neutron stars to start getting the things many of you want, gold, platinum, silver, okay. Okay, so our goal is simple. We actually conceptually now have a reasonable understanding how we went from a hydrogen-helium universe to a universe where chemistry becomes possible, okay? And our goal right now is, can we actually quantify and say, what is the fraction of, let's use, maybe, let's use carbon, because the ratio from iron to hydrogen will be a bit too small. So, for example, right now we know carbon, nitrogen, oxygen. These are the most abundant. Believe it or not, astronomers call anything other than hydrogen and helium as metals. Okay, now if you're a chemist, you may have practically a heart attack at this unusual definition. But these are, let's see, oxygen is about 500 parts per million with respect to hydrogen. Carbon is 300, nitrogen is 100, okay? So we want to understand why this fraction. That is not just the periodic table. What is the underlying ratio of elements. Okay, that's where we are going on this. Okay, so it's giving a quantitative basis to the fraction of elements in the periodic table. Okay, so I would say that there's a general understanding of this, and now for the next, many decades, or hopefully perhaps even less, astronomers will try to explain these ratios. Okay. And that would be a grand quest and a completion, and we should be really amazed that sitting here on Earth, we can actually tell you how the universe periodic table got built up. I mean, this surely has to be far better than a Shakespearean play by a long shot. Okay. So now let me tell you how this project came about. This is more, now I'm switching to sort of the how do these projects get started? So this part is really more for ambitious graduate students, maybe ambitious assistant professors. As I told you, ideas are cheap. They're obvious. You have to take these ideas and execute them, and there's a lot of things there. That is real life, and there are many. And that's something you're not taught in grad school. And that's one of the main advantages of coming to a lecture like this, is you sort of understand how these things get done. You attend enough lectures, then you'll start formulating your own policy of how to go about it. Anyway, so I have a habit, which I mentioned with no prejudice, that I like to switch subjects about every 5 or 8 years. Mainly because I'm very curious, but once I understand something, and I've written the first 5 or 6 interesting papers, usually in Nature, because you don't have to pay money, and then I say, yeah, I'm done, I move on to the next thing. So in the early 90s, I wanted to learn X-ray astronomy, because I started as a radio astronomer, then went to Caltech, became optical. I said, okay, let's do X-ray astronomy. It's a new thing that's happening. So I went to Japan. Professor Tanaka was a major figure, and he said, yeah, come, we'll be a visiting professor, and you can learn about this. So one of the things, if you want to switch subject, want to do something new, there's an old statement, sometimes attributed to Feynman, which says, if you really want to understand something, you should teach a course. Okay. And I love that, because I decide, okay, I want to get in this field, so I first teach a course. First year, it's like a surgeon, You learn how to do surgery. First patient, good for surgeon, maybe bad for this patient. Second time's roughly equal. Third time, surgeon's getting bored, because, God, how many times do I keep cutting up these things? So I only teach a course 3 times. After that, it'll become boring. Anyway, so I start teaching informally a course to X-ray astronomers on X-ray astronomy, because there's nothing like actually going and telling people, okay, I don't know much, I'm going to teach you a course. You're right there. You're naked, intellectually speaking, and suddenly you're challenged, okay, which is a good thing to do, okay? Anyway, and then I actually realized there's a whole field which I didn't know called gamma ray bursts. I said, and I'm fairly good at actually figuring out sort of where these trends are. And I thought this whole community wasn't exactly knowing how to do this problem correctly. Anyway, so I got into that field, and our group was able to resolve a 30-year-old mystery about the origin of gamma ray bursts, and showed we were able to find the brightest GRBs. We were able to show the connection of gamma ray bursts to supernovae, and so on and so forth. So that was due to so by about 2004, NASA decided they launch a big mission called called SWIFT, which is going to find, instead of 1 gamma ray burst, a month that Beppo-Sachs was doing, this would be like 100 a year, so 1 every 3 days. So I was on my way back. I'd gone to the launch at Cape Canaveral. I was coming back in November, and I was thinking, okay, this is the time to leave the field, because now everyone and their brother would be working on gamma ray bursts. It's now very common. And I didn't know, so I started thinking what to do next. And I decided, okay, I should teach a new course. And so I taught a course on high energy astrophysics, because gamma rays had introduced me to this general idea. And so during teaching that course, I came to realize that if these two neutron stars, they coalesce, okay, it's a very complicated problem in nuclear physics. Let's see, are there any grad students in physics here? Okay, very good. Let's see. So, okay, you're ready. You please be preparing a bit, okay, mentally. So you have a neutron star, and neutron stars are made of neutrons, as they say. Okay. Now, if I take a neutron and leave it in this room, okay, how do you think it will be stable?
No.
What will happen?
Maybe it joins other particles in this room.
Okay, anyone wants to tell me what happens to a neutron if I leave it in this room?
Neutron decays.
Into what?
Proton.
And that's it? Okay, very good. And is any energy released? Anyone? Maybe, or no energy released? Okay. I'll be honest now. You want to be a physicist or an astronomer, you've got to have these numbers in your head. Okay? So please, lesson number 1 for grad students, you have to know these things. And it may mean getting up in the morning and memorizing these things, because if you don't have the numbers, you don't know where to go. Without numbers, you're lost, okay? So it takes about 10 minutes for the neutron to decay, and the average energy released in the beta particle is about 1 to 1.5 MeV, which is a rest mass difference between a neutron and a proton, okay? So I was thinking of a very simple problem. I said, okay, let's say we know the idea is that the neutron star is 1.5 solar mass, this is a 1.5 solar mass, and we believe the maximum mass of a neutron star is 2 for some other reason. So that means most will go into a black hole, but there'll be a small amount of the debris still left. Okay, and now there's a very complicated problem. If you take these neutrons, which are not decaying, now I won't put any of the grad students in spot because it would be bad spot actually, asking why doesn't a neutron decay in a neutron star when it's decaying in the room, okay? Anyway, okay, so, the few debris left over, the neutrons start decaying in 10 minutes. Each decay is supplying about 1 MeV of energy. So, and this is a somewhat easily computable problem because of an exponential decay, so it's actually a semi-analytical model, and I thought I'll give this as a question to my class, as a homework. And then after a while I realized, is this detectable? And I was surprised, is this actually detectable? Because one of the things that I'm telling you is that all the things, anytime you compute, you should know the numbers and say, is this detectable or not? Is this observable? Is this measurable? Then I decided I'm not going to give this interesting problem to the class. I'm going to write a paper on this myself. Okay, anyway. And then I realized they actually would lie somewhere here in between these two things. However, this would require, it'll be faint, it'll be fast. It won't be 10 minutes because of the diffusion of these photons. It'll last for a few days. So in literally a couple of days, you have to survey the whole sky to a very high sensitivity. So it required a machine at this point, which we sort of didn't exist. And I was thinking about this, and I saw in one of the chit chats astronomers doing that, there's a new transient discovered in this outskirts of a galaxy called Messier 85, and the people who had discovered said, "Oh, it's not a supernova. It's too dim to be a supernova, underluminous." And I knew right away. I was absolutely right on. Okay, there's stuff in between novae and supernovae. So I called them up and said, hey, that stuff you guys are not interested. Look, why don't you give me the data? I'll write a paper and it'll be to Nature and you can be happy. They said, fine. They didn't realize what they were giving to me. Okay. Anyway, so I wrote that paper and another thing in Nature and I'm done with it. Okay, so here. So that's what I'm telling all of you. You should have this ability to compute this on the fly as you're listening to a colloquium like this, okay? Okay, good. So the question is now, there's not only a concept, but I knew it works, how to do this. So I was talking with a friend of mine, Lars Bilston. He's the director of KITP, the Kavli Institute for Theoretical Physics in Santa Barbara. I was telling, Lars, I have this idea. I think we can, most of the way this is being done in the community where there's a grad student who's observing it every night, and morning they look at the data, difference the image, and see if it's a sort of a slow process. I said, what I want to do is in a completely industrial machine, okay? Being trained as a radio astronomer, I have no love for the idea. Many optical astronomers are very different people. They actually think it's very romantic to go to a telescope, open the dome, maybe like Professor Chu was talking about, he's a sort of, I think, a little romantic sort of guy. I don't care. I'm not at all interested in observing late at night. I want to build machines because I want the data. And I really don't particularly like to stay up at night. Anyway, so I said I want to build a machine that will do this industrially, not by 1 or 2 grad students. In fact, no grad students, because the highest efficiency has no people, okay? So he said, fine. So he said, I want you to meet this person. So we had a lunch here in the wharf at Santa Barbara. Supposed to last from 12 to 1. It ended at 5. The next day he called me up, Wayne Rosing, and he said, Shri, I like your idea. In what way can I help you? I said, okay, Wayne, give me $1.5 million and 6-month option period. So let me explain what that means. I said, in 6 months, I will double the money by commitments elsewhere, which means this is a strong idea. Other people are willing to put up money. And if not, you take the money back. Okay, it's very important to stand out. If you believe in something, go for it 100%. And if I couldn't double it, perhaps not worth doing because I couldn't even get the buy-in of other people. Okay, so 6 months later, I came back. I had institutes around the world. Okay, various people with startup money, they're all very enamored with this idea. So we started the Palomar Transient Factory. And the way this factory works, and this is the concept of a factory, is how do you get high efficiencies? In a car factory, you have a line. There's one place you only make fenders, another place you only make wheels, and so on. And there's a line that moves, and you assemble it. Okay, so the idea here is take the 48-inch telescope, which has a very large field of view, image the sky with a large detector, use the 60-inch, because this will produce a large number of discoveries in a night, to do some color sorting, which will give you a little clue. Is this a flare star, which is very common, an occasional nova, and a supernova is the most rare one in this. And sometimes you see changes because the object is moving. So if you observe it a little time later, it won't be there, so that you know right away it's a moving object. And so dedicate these two, okay? And so I have a habit that when I take students, first of all, I really like to take students who are better than me. Usually that's the criteria. I say, are you better than me in something? Yes. If not, okay, find someone else. And even within that group, I'll say, if you're really good, then I want to give a very high-risk project. Because if it fails, that's very good student can recover. So anyway, I found a young student, and I said, okay, chance this will work in your thesis is maybe 10%. If it doesn't work, there are a few little papers you can write up. And now, later, she went on to become a professor at Caltech after going somewhere else, coming back. The final test is to use the 200-inch for spectroscopy, which gives you a very clean signature of what is the explosion. Okay, this project was put together with only young people. I hired Nick Law. He had just finished his PhD at Cambridge, UK, and he was a project scientist. It's a very big role. Project scientist ends up doing all things not done by others, okay, and gets all the blame when things don't work. Perhaps the worst job was Robert Quimby. He had finished his PhD at Texas, Austin, and he was the software lead, which means he had to integrate software from all other parties. And many astronomers don't write very good software. They think they do, but they don't, okay? And Eran Ofek from Tel Aviv, he had finished his PhD. He was in charge of all robotics and all the algorithms, okay? Then I had a couple of older people, our chief engineer, COO, Rich DeCaney, Peter Nugent, very experienced in data reduction pipelines, Jason Suresh, and Josh Bloom, who had worked with me before, had gone off to Harvard. And he had some ideas of machine learning, which I was very suspicious of. I said, why don't you come and prove to me? Okay, so this is back in 2009. Anyway, we achieved first light, and it's a massive software project with lots of algorithms, and there's no one in the loop. This is the 48-inch has not only a sequence, it's like you say, okay, how do I observe? So we had built a program which sequences itself in the sense that, if you say, on an average, I want to do this. But there's weather, there's something that goes on, and you don't want to sit down every night or afternoon and fix it. Okay. So data flows to Caltech. Real-time pipelines have to be robust, or there'll be glitches, so they have to recover from that. And the image subtraction then came an important problem, which is, so here's a new image and here's the old image. You subtract the two, and you can see slightly brighter here, and in fact, it shows up here. Your eye is very good. It says, yeah, that looks pretty, what's called clean subtraction. Occasionally, here's one, subtract, but now your eye starts seeing little fuzzy things here, and then there's some of this fuzzy thing. The chance that two supernovae is small, okay, very rare. So this is bad subtraction, and that's what the human eye is very good at. And so Josh Bloom brought in machine learning in 2009 that eliminated the whole human thing, which was a very painful step. Okay, so at this point I had to go a little bit more technical. So PTF began, and one thing you have to understand is that I have a very strong view that when you do a project, the first thing I want to ask is, when is it going to end? And you said that's a very strange way of looking at things, because most people want to run projects forever, which is fine. There's a style of doing that. The reason it's good to ask when it's going to end is it sharpens your mind. If you know you have only so many nights, it'll tell you exactly your priority of science. Otherwise, if you think something's going forever, you want to do everything, and you can't do everything. This is called an opportunity cost. When you decide to do one thing, automatically you're not going to do n-1 things, and most people don't understand this concept. It's the absence of not doing that is very hard to grasp. So you have to choose carefully that one thing you want to do after consideration. Anyway, this was supposed to last only 3 years. I said, yeah, 3 years is fine, then we'll be done. There's also a competing project funded by Air Force at a very high level of funding. I thought they'll come and beat us for sure. But it was so successful that it led to Palomar Transit Factory 2, or the intermediate trans. So we did a whole bunch of, a lot of technical stuff here, okay? And finally, in this we realized that the spectroscopy is very important, but most spectrographs are run by people. So we, in fact, not invented, we designed a spectrograph that actually doesn't require pointing very precisely, which is called the SCDM, and that's turned out to be a marvelous success. A 60-inch telescope at Palomar does as much classification as the rest of the world. Okay, so so as this project came along, we machine learning. I was I was a little skeptical, but now wholesale we are not into machine learning is old. Now we're into AI stuff. Okay, that's all. This is, and each of these have various student projects. Okay, so the Zwicky diagram is now quite rich. Here it was at the end of PTF. We had, we had this novae, but then we found this luminous red novae, intermediate. When I say we, there are other projects too going along, but we are like a major player. Calcium, things which are rich in calcium, supernovae which are extremely bright, and then, things related to gamma ray bursts. Okay, so you can see our jungle is getting richer right now. The phase space is larger, both in X and Y axis, okay? Okay, so the success of these two, and I was like, it's one of these things you say, oh my God, we'll be done, and then let's move on to the next thing. Is the success was so much that we actually saw an opportunity to do a survey before a major international project called large survey, LSST, the what becomes Rubin Observatory. It's going to cost $1 billion, it'll be bigger, blah, blah. So, And we thought, okay, why not propose this as a precursor? And NSF liked it. So this led to ZTF. It became a very large project with people around the world. You know, there's all the way. We can start here. This would be at Taiwan. Then it goes through Israel, you know, in Germany, UK, France, then some laboratories in the US, institutions in the US, okay? And so what we built here was a camera, and the person who led the whole camera project is right here, Roger Smith. And this is amongst the world's largest camera. It's the most compact one. It's the by next year, I think there'll be a larger camera for LSST, but we were there first for 10 years, so I'm happy. But as you can see, I'm somewhat competitive about these things. Okay, so our camera, we want to decide it's got a large field of view, and that's the LSST camera. It has a smaller field, but it's on the bigger telescope. Here's a Japanese telescope, 8 meter, very small field, but beyond 8 meter. So it's the opposite. We decide to take our weakness. Our weakness is with the smallest telescope on this diagram. Okay, what do you do if you have weakness? You find something which gives you compensation, so you've got the largest field of view. So our goal was to go and do the brightest things in the sky, which is a good idea because the bright stuff is easy. And so you do all the bright stuff, and when the going gets hard, there's faint stuff, then leave it to other people to clean up. Okay. This is a very large engineering project, now not just in a software sense, in a hardware sense, and we had to essentially redo the whole, Professor Chu was saying these old telescopes, yeah, we had to almost redo the whole thing, okay? So I'll just flash through this, what all it took to take this old telescope and completely modernize this. And here's this amazing Roger Smith camera that I was talking about. And here it's actually what it looks like. It's got 16 absolutely top grade, science grade CCDs. These detectors are nothing like the CMOS detectors you have in your cell phone, which are actually pretty good. I'm not mistaking about that. So I'll just flash through this, just to give an idea that these sorts of things are enormous amount of work. And that's what I'm saying. Ideas to execution. Idea is simple. Execution, it's not at all. Okay, here it is. Okay, finally gets installed. Yeah. And then it's got a robotic arm, which allows you to insert filters because this old telescope, we have no room. So we had to be a little clever about that. Then we had a problem. It required a corrector plate at the front. And the vendor, a small company in the east coast of US, who we had promised $300,000, he said, well, he got a bigger contract and he's going to put our in a slower schedule. But this was now what's called in the critical path, okay? That meant he was limiting our thing. When you have a project like this, there's so much hardware and software all being done. You're paying all these people. It's called a marching army cost. So if something happens a few months before launch, as it were, you're paying all these people. And you can't say, I'm not going to pay you, because they'll go do something else. And then when you want them back, they'll not come back because they're doing something else. So you have to pay even if they can't do anything. And this, I thought we're going to like dead, okay, because usually this is how you go bankrupt, okay. And fortunately, I have many friends in China. I'd been visiting China, and then one colleague, NIAOT in Nanjing came through, and they made this aspheric in just a few months. And so I said, okay, we had set aside $300,000, we'll give it to you. And they said, no, we don't want that. We only spent $60,000 for the material. Then I said, well, okay, I'm just telling you what it. Said, instead, we want you to take 2 students every year in summertime and train them. Well, that's easy. Each student had to pay $5,000, so it's times 10 for 5 years, $50K. I'm like, $300,000, $50K, I win. And then I got these students, and some of them turned. I said, it's very simple, because I don't like to work with, I have a simple rule. It's got to be very good students. PhD is not for everyone. In fact, it's for very few. I said, you have to make sure that you conduct exams or interviews and send me the 2 best students in China. And it really worked well. So I got some really amazing students. Yuan Yao just finished recently, and he's done spectacularly well. So I had a number of very spectacular Chinese students. Okay, here it is. We got first light, and this is Orion. You can see, I know in Hong Kong a bit hard, but it's a large field. And all the software until then had been done by students and postdocs, but this is a new level. So we went to a professional data service, which is inevitable in this. Fortunately, Caltech has such a place called IPAC. And we got some money from the Heising Science Foundation to do the science. And we use a lot of follow-up telescopes around, not just our own telescopes, but in Hawaii, Keck, radio telescopes, northern hemisphere, southern telescopes in space. And here's the final product. Okay, let's see, does this work? Play. Yeah. Okay, so what you're seeing here is that's the date, okay? And that's the number of supernovae by that date. So the survey that when we started PTF, the big survey was 100 a year, okay? Now we basically have the ability to discover, or we have but we don't follow up, maybe of the order of 20,000 a year, of which we classify 2,000. So we've completely changed the game. And there are different kinds, exploding white dwarfs. These produce ion collapsing massive stars. That's sort of the oxygen, the intermediate mass elements. And these, I don't know, they're sort of a new thing we still have to understand. The reason you don't see any supernovae here, this is the Milky Way. This is the dust in a galaxy. So this is done in optical, so they're obscured. And we don't see anything here because it's the southern hemisphere. So if you're in the north, you can't see in the south, Okay. Okay, if you have a large discovery rate like this, you can occasionally find some, unusual events. So here's a fun one. So imagine a supernova. Okay, here, it's us shown here by Hubble Space Telescope. And there's a supernova in this galaxy. Let's say, but the line of sight from this galaxy to this intervening galaxy just so happens, let's say, they're all on the same line. Okay? What's the chance this happens? Turns out to be 1 in 1,000. Okay. If that's the case, then the rays coming from this supernova, this ray would have gone ahead straight. We wouldn't have seen it, but it gets bent by the gravity of this thing. So you'll actually see what's called gravitationally lensed images. Okay. And this lensing for this case was about 52. It's a big number, huge lens. But here's the one I like the most, which is the destruction of planets. So it sounds a bit morbid. The sun, in about 4 billion years or so, will expand and become a red giant. And as it expands, the planets which are close in will get devoured by the sun. They'll evaporate and get destroyed. It's amazing. Now there are some fraction of stars which have Jupiter-sized objects, but closer than our Jupiter. So they will create actually a rather strong signal, and we actually find them, okay? We find them. This is a cartoon, of course, but we're actually seeing stellar destruction happen. So we now find we have a little cottage industry of finding planetary destruction by the host star. Okay, so lots of, I can't summarize this project in such a short time. But I would say perhaps the most equally valuable contribution is at Caltech alone. There are 12 PhD students, or altogether 12. So 12 PhDs, about 12 postdocs. And the team has published about 220 papers in 6 years, which is not bad at all for this group. But the best part is because we put out this data in real time, the alerts and all this data services, there's an enormous publication by the rest of the world. Of course, we are not authors on that, which is fine. So what this I call is the halo factor, okay? So it's like, how much did we produce, which is directly the papers we've written, how much did the others produce, and then we're shining in their reflected light, okay? So our halo factor is 4, which is pretty good, okay? Which is the reason maybe I got the Shaw Prize. Okay, so, and then we also contributed, Josh Bloom, he used his expertise and started a company, Wise.io, offering machine learning solutions to real life, and then he sold his company later to GE when the stock was still high. He made a ton of money. I know that because he's a professor in Berkeley and he has a house on the hills overlooking the Bay Bridge and Golden Gate, so he must have done very well. And another company called Soroco.com was started on the idea of software automation when I gave a talk, the ZTF concept talk at MIT in 2013. Other members have gone out to startups, Weights and Biases, this new startup, Google, and so on. Okay, I'm very happy about that. In fact, my thing is I want most of my students to go and do this, and then I want them to remember something, that to send me back 10% to do research. Okay. Okay. So we started with this diagram, and it's now become very complex. It's an host thesis topic, and there are all sorts of things which I won't even try to explain to you, okay? So I started with the concept. My view was, I want a machine, here's my idea was, I come in and say, okay, the problem is straightforward. Things are changing in the sky. I want to see what they are. Okay, it's a well-posed engineering problem. So the idea is I come in and say, machine what have you done in the last night? And it is rank ordered. Here's the most interesting thing. Then I sit down and write a paper. I call that as ZTF, phase 1 or something. Then after a while, I get tired and say, okay, phase 2. I come in, and the machine has rank ordered, and then use ChatGPT and already written the paper, okay? So I'm on my way for this quest of the totally automated discovery of the universe, okay? And we have achieved a bit of that. So here it is. So last year, we reached a level of automation. Okay, this is from the team. We present the classification of this supernova as a type 1 supernova at this redshift. To the best of our knowledge, this is the first transient which required no human action from its discovery to spectroscopic classification being posted to the transient name server. No human were involved. The telescopes ran robotically on sequenced things. Pipelines ran. Algorithms identified high-value things. And then it sent, rank ordered, sent it to another telescope, got a spectrum, it then AI classification of the spectrum with enough confidence to report to the world and say, we have discovered this. Okay, we are almost there, right? The only thing now is how to use ChatGPT. Okay, so, and write this paper. So let me end at this point. Okay, this was a great project. This is my backyard. There's an orange tree, and when the oranges flower, when you have a situation like this, just go for the low-hanging fruits and leave the other fruits which require ladder to better people. Thank you.
Thank you, Professor Kulkarni. Please take a seat at the center for the Q&A section. May I also invite Professor Chiu to moderate for the Q&A section.
Okay, thank you for such a fascinating talk. So we are going to open up for Q&A, but I take the privilege to ask the first one. So earlier you mentioned, and I was really fascinated by your style. You go into a project and you look at the end date and then you jump to a completely new project. You learn the stuff, you teach a course. To many people, that would be a very risky way, risking your career. And particularly for us, Hong Kong people, we're very conservative. Why do you do such risky thing? And then later in the afternoon, I also heard you saying that this might be a good idea for some people, but not for other people. So I'd like to hear you elaborating that point.
There are 2 points I'd like to make. One is it's very simple, okay? High risk, high gain. Yeah, fine. If you don't want to take, if you don't do high gain, or you don't take a high risk, you'll. So I'm saying all choices have consequences. What is not allowed in this is to say, I want to be a great scientist, but don't want to take risk. I said, oh no, you have to choose one or the other, okay? Now, there are many ways to be doing forefront research, okay? I would hardly say the approach I have taken is the only way at all. In fact, I would say it's a bit off the regular track, and so some problems really require you to focus and gradually build up over a 30-year period, maybe. Like, look at LIGO, okay? The Drever and Weiss and Kip Thorne, they had the idea, the ideas were straightforward. In the sense, in the 60s, the ideas were known. Einstein's equation, this produces, and the idea of two neutron stars were discovered late 60s. 1975, Taylor and Hulse discovered a binary pulsar, and you could measure its orbital decay, and you knew it's going to coalesce. That means it's going to generate. Okay, I don't think someone like me would have been well suited to be any of those three gentlemen, because I just don't have that temperament. I can tell you that because I once foolishly tried something, and then I realized who I really am. As a graduate student, I had the amazing luck and fortune of discovering the first millisecond pulsar a year before I graduated. And then many people said, Shri, you've got to do pulsar timing, because it was very clear right away, within a year. A great paper by Hellings Downs was published, which said, these are precision clocks at the atomic level, but in inertial frames. So this is a really great way to start looking for long wavelength gravitational waves, which are either generated by the early universe or, as later has become more common, supermassive black hole binary systems. So I used my prize money, I had gotten a big prize, and to invest into building very high speed electronics to do wideband pulsar timing. After a year or two, I realized, that I would have to do this for the next 30 years. And I said, no, I'd rather shoot myself at that point, because it's not me. So it's one of these things, there is glory, there is this stuff, but it's not you. You should always be true to yourself. So, but 30 years later, now, other groups which have been there, they are finally detecting, which I think is an amazing discovery, that you can start sensing gravitational waves from supermassive black holes. But that required, like LIGO, a long investment. So you should figure out who you are, if you want, and what problems you want to solve. I have a simple view. I don't particularly care at all which problem I solve. I find everything's very interesting. It's only a question of what I think I can do in a certain time scale and get away with it. That's the reason I wanted, when, for me, the brown dwarf discovery was a dynamic range problem, and I was very interested in certain things, and it led to a discovery. So I think the first step in a young person is to figure out who you are. Are you a conservative person? Fine. Then better choose a long-standing problem and be at it. But if you're not, well, then take advantage of this. So I don't see any conflict here. But what doesn't work is you can't just say, I want X of this, but really that outcome. That doesn't work.
Great, thank you. Okay, let's open up for questions from the audience.
Okay, if the grad students don't ask questions, then I'll ask you a question of why neutrons don't decay in neutron stars. So you better ask rather than being pointed to an answer.
Okay, that's a question in the back.
Good afternoon, Professor. I would like to ask that you have mentioned data and throughout the talk, but I would like to, since I study chemistry, I would like to ask, and I'm currently studying how to use instruments to analyze some data, perhaps spectroscopic data. I would like to ask how important is that in terms of discovery, your discoveries that you made in terms of analyzing the data or generating the data by using instruments. And also on a personal note, finals are coming and I don't really have the motivation to complete homework. I would like to ask, how do you have motivation to do stuff? Like, do you just wake up and say, I'm gonna do something? Or is there a process that you have to go through? Thank you very much.
Okay, let's do the first one. It's a bit easier. So what's happened is that this phenomenologic subjects, there's been a massive change. So let me start. The two subjects which have changed enormously that I'm somewhat familiar, of course, astronomy very familiar, but familiar with also in biology, is because these, amongst the subjects that we have now, biology and astronomy are the largest producers of data, okay? But just 30 years ago, that was not the case. We'd all go to our telescopes, we'd get 2 or 3 nights, or if you're the radio astronomer, 10, 20 hours. You'd bring a magnetic tape home, and you'd guard it preciously because you could only study a few objects, get a few spectrum, and so astronomy has really gone from a data-poor subject or data-limited subject to a very large data subject. And it is not particularly by design, actually. And many people have wondered, this is a major topic, many people have thought about this problem. One of the reasons, it just so happens there's a confluence, the technologies for all this large data production is the same. One is sensors. We can just, sensors, computing, and transmission of data. All of that is the same underlying semiconductor technology, and that's been following Moore's law essentially for a long time. Okay, some a little ahead, like sensors are the last ones, transistors are the first ones. But as a result of this massive growth, astronomers produce data because we can, that's all. Whether we had anything in mind or not, I don't know, but we can. As a result, we've gone from data poor to data rich. And in fact, my view is that data production of the sort, so when I see young students, I tell them, no, we don't need many data producers like me. I feel like I'm now a little bit of a dinosaur because that is an era where hardware and instruments, all that dominated. That was a limiting step. But now, our field in astronomy is awash with a large amount of data. So if you're very clever in extraction and analysis of that, that is where the future is. So if I'm young all over again, okay, I would sort of refashion myself as some sort of a data scientist, because I think the opportunities are very high there. There'll always be a need for new instruments, better sensitivity, wider field. There's always be there. But I think you need fewer people to do that. Okay, and the second question, you said you're not motivated.
Yeah, I'm not motivated.
Well, okay. Can I give you a very simple and a clear answer? You won't get upset. Okay. If you're not motivated, why are you here? Okay. No. Look, you're an adult, and you should. There's only one life. I don't believe in other lives, so every day counts. Every day counts. You have to take it absolutely seriously. And I know when you're young, it looks life is forever, but every day counts. There only maybe you shouldn't be in a PhD program. That's what I tell you if you're my student. And then maybe you could go and become a great entrepreneur and then send me back 10% because of the advice I gave you.
Also remember, there would be no chemistry without stars. Okay, there's another question in the back.
Hi, Professor. Thank you for the talk. So earlier you mentioned somewhat the lack of progress in the study of dark matter. Part of my study subject is involving dark matter. So in your opinion, is there some fundamental change that's needed for this field to progress, or is there something wrong that we think about how we study dark matter?
This is a subject, dark matter, dark energy, something I think a lot because I find it very fascinating. It's one of the most outstanding puzzles facing science. It's really strange. Most of the matter is not ordinary matter, and we are part of that ordinary matter. So we are sort of, in a kind of a universal way, we are this little something that doesn't matter to the rest of the universe. So it's very fascinating. Yeah. So if you can solve this is what I call a. I'm a very practical guy by nature. Okay. So all decisions I take are very analytical. I don't understand the concept of people, thinking by emotion. So when our two daughters are sitting here, when they're teenagers, I said, if you want to marry, you should set up a little spreadsheet and analyze, which is fine because people you marry, it's a very probabilistic thing. So it's not some divine thing, So anyway, we can talk about that later. So I'm saying you've got to analyze this. You have to do a cost-benefit risk analysis. What is the cost? What's the benefit? What is the risk? The benefit of figuring out dark matter, I would say, is enormous. You'll be given 10 Nobel Prizes in the same year, okay? What's the cost? I think it's very high. Risk, extremely high, okay? The reason I have no idea of working dark matter is I don't think any of us know which way to proceed. And my problem with that field is people pretend they have signals to go. Okay, so let me first give a simple analysis first. So, pulsar timing, okay, one of the things is verifying gravity. People there's a whole industry, it's called, I want to do precision test of gravity. Well, it's a good thing. We should do precision test of every physical model until it's hopeless to do any more, right? We don't do precision test of electromagnetic theory because it's been verified to very high precision. So gravity, general theory of relativity, yes, we should do that. So let's say there are two binary pulsars which have been discovered, and so you can do really very precise tests because there are two clocks going around each other. Then you can say what are the free parameters, M1, M2, inclination, eccentricity, okay? And what are the physical effects, precession of the orbit, orbital decay, spin-orbit coupling. So you can start putting these constraints. And what you find when you do this is all these constraints lead to a small chi-squared region whose reduced chi-square is 1. What does it mean? It means there's no information left. That's what chi-square 1 means. Reduced chi-square 1 means that it's all stochastic noise at this point. Yet there are maybe hundreds of physicists who want to have alternative theories to gravity to come say, oh, but if we added this other tensor field or a scalar field, then put an alpha in front of that, which is the strength of that. And then we can analyze this data and find that alpha equals 0 plus or minus 0.1 or something. I would say this is a complete waste. It's not even science. Okay, because if you want to propose a theory alternative to GR, it should be a better theory. It should satisfy all the expectations of a physical model. None of these models are actually that. They're just adding stuff. So all I'm saying is you need some direction to know which way to go. Science works by directions provided by the world or by the universe. You measure something. So Einstein said, okay, the perihelion shift, of Mercury, that's a clue. So now you know there's a direction. If you have no direction, why are you working on that problem? I don't understand that. And I think this disease, I would say, that physicists, theoretical physicists have actually, and hopefully there are not many in this room, and actually it'll be fun if they have them actually, in many ways, is because of the success of the standard model. The standard model was so successful that many people think that a mathematical understanding a mathematical approach is a winning approach. Einstein is amazing scientist, but also a very bad example because everyone thinks, oh, if Einstein could sit in his room and figure out special relativity and GR, why can't I do? My answer is simple. You're not an Einstein. Okay? So, and maybe it's a fluke. Okay? But this idea that we can sit around and with no clue from actual evidence and come up with the theory. I don't buy into it at all. And that's the reason this field has zero progress. If you ask what is dark matter, 20 years ago, it was all supposed to be actions, okay? Why? Because some Nobel laureate said, oh, well, if you have this sector, it will be complete if you have actions roaming around. Well, okay, 20 years have gone by. Now people say, well, dark matter can be anything from, black holes to all the way to, extremely low energy, de Broglie wavelength the size of the galaxy. Why, including dark avocados, I suppose, in between. Well, that means you have no clue. So on what basis are you going to choose to work, especially if you're young? So I will make a very strong statement. If you're young, don't work on this problem unless you have some clue which says, I know which way to go.
Okay, next question.
Thank you, Professor. Thank you for a very nice talk. I was just wondering, when you first developed this transient factory, what makes you think that this is a successful idea? Because now that you have such a huge amount of data, you need to develop so much techniques to handle them. But at that time, you don't have any of those techniques. So what makes you think that this would become it would become a successful idea, but what makes you think that it was feasible at the first place?
Well, no, that is success, I don't know. But once I had this idea that we can even see this the slightest radioactivity, which is neutron decay, if that is actually detectable or within reach in some assumptions, that was a concept, okay? It's an idea. And I told you my view is ideas are cheap, okay? But once I found this other object that the Lick Observatory people had, which was in between nova and supernovae, I knew doesn't matter. My initial motivation was a simple and semi-analytical problem that I could solve. The fact we found something else means nature is rich, okay? So this is not a will-o'-the-wisp. And the other reason I wanted a 3-year period on PTF is, yeah, it's not successful. It's better to start out and say, let's do it for 1,000 nights, and the end of which, one of two things. Either you're very successful or you're failed. It's best when you collect money from other people, say, we're going to do a 3-year thing. Let's see where it goes. And then there's clarity. If it fails, you say, yeah, we did something. But that's what I'm saying. You've got to do a cost-benefit risk analysis. Okay, so you have to constrain your cost. And the way you constrain your cost is to tell and to yourself and others, people who fund money, give ideas saying, it's an experiment, let's try 3 years, at the end of which either we'll have a party or a wake. That's it. But if you tell people, let's do a 10-year project, let's get $100 million, and then we will succeed, you better know what you're doing. Okay, I'd like to get some questions from girls and women, please. You're not here.
I've been wanting to ask this one for a while. I haven't been able to ask it, so. All right, so what I wanted to know is, you said that the machine learning process was quite, it was a difficult choice. And now we've reached a point where there's a lot of utility for using AI in many fields. When did you guys know that you had something with AI where you said, okay, we've got it to a point where it can reliably distinguish sort of supernova from not supernova?
Okay, so in 2009, when Josh Bloom said he could do with machine learning what we are doing by eye, and it was not, initially some of us were just, in the team looking and saying, yeah, real, not real, okay. And in fact, Josh's program is called as Real and Bogus. And then we had a group at Oxford University doing citizen science. That is, would ship out this data to Oxford, and they'd distribute it around the world where people would actually, after being trained on a little tutorial, would make these choices. Okay, and the next night, if large number of people voted in the previous night, this is real, then we'd observe that on the 60-inch, because we couldn't observe all the discoveries of the previous night. We'd observe that, and then one of two things. If the classification was bad, we'd know the answer. So what I told Josh is, we'll run your project for 6 months in parallel with the citizen science, at the end of which we'll know quantitatively how well you're doing. And in fact, I can tell you that the false positive, what is called a ROC analysis, was that the human eye was still superior by a factor of 10. I don't mean, it's not, okay, I should be very careful. That you can make an error of two sorts. Even when something is not there, you can say it is there. Or when something is there, you say it's not there, okay? And we want a very high level of performance here, okay? We don't want any false things, okay? And we want all real things. So we are already at the 95% level of performance, but we are trying to reach 99%. And then, this showed this is pretty good. So Josh's stuff was showing maybe 1 in 100 times we would make a mistake, which I think is very tolerable. So at that point, we said, okay, we'll not do this human stuff anymore. And then every year we held contests amongst various computer scientists, real bogus challenges. And at this point, this real bogus is actually performing or maybe even slightly better than humans. So yeah, then it's done.
That's a question.
So thank you, Professor, for the talk. I would ask about, you mentioned science has two approaches, which is one is phenomenology, and so do you think there's unlimited of phenomenon that the universe remains undiscovered, and do you think the human capability is unlimited to find all of the science knowledge?
Well, I can tell you history-wise, people who have said this is the end of science as we know have consistently turned out to be wrong. Okay, so I forget, there's a very famous scientist who just before quantum mechanics was coming said, we know all there is to know, and well, that was a few years before quantum mechanics. So I'm pretty sure the universe, look, it's very simple. The universe has been around for 13.4 billion years, okay, which is a very long time. Our own galaxy has 100 billion stars. There are 100 billion galaxies. Most of the stars are not single. They have binary, triple, which means they have. So the number of combinations of outcomes in just astronomy far beats the number, sand particles on this Earth. Okay. In fact, you can almost say that a triple star anywhere in the universe is different from another triple star. The outcomes are very large. So when we say we understand, it means we understand something at a certain level. So the universe is a very rich place. And think of, just on the other end, think of chemistry. Chemistry, like biochemistry, is very low energy reactions. The energy exchange is not in 1 electron volt. So the complexity increases enormously. So you start with something like very simple ideas in molecular biology, and you get very complicated outcomes, including, emergence of intelligence, which seems, very remarkable. So if you're not impressed with the universe being rich already in biology and astronomy, I wouldn't know what else to say.
Okay, that's actually a very good way to end this session. Unless I see a last question from one of the female students, you're privileged. Okay, if not, let's thank our speaker again for a wonderful talk.
Thank you, professors. May I invite Professor Freedom Leung, head of Shaw College, to present our token of appreciation to Professor Kulkarni and Professor Chu. Professor Kulkarni, please. Then we shall have Professor Chu. Thank you, professors. May our honorable guests take a group photo together. This is the end of the lecture. Thank you for joining us, and we hope you enjoyed the lecture today. Thank you.